Can everybody hear me? Well, welcome back to CPP today. I'm happy to see so many of you made their way here. Didn't have an invited talk this morning because the invited speaker was sick, but we'll have an exciting talk today because Jannis is going to talk about Aesop, white box, best first proof search for lean. It was one of the distinguished papers we have, so I'm really looking forward to your talk.
All right, thank you so much for having me. I will indeed be talking about Aesop, a new proof search tactic for lean. The general flavor of the tactic is very similar to Cog Auto or Isabelle Auto. So you can think of it as Cog Auto with a few bells and whistles on top, or Isabelle Auto with a slightly cleaner design. I'm going to show basically two things in this talk. First, Aesop's basic approach to proof search, and then how we extend this proof search with support for metavariables, which turn out to be fairly non-trivial. So, Aesop's basic approach to proof search. So, like I said, it's very similar to Cog Auto and so on. So, the general concept is users define a set of rules that Aesop then applies to the initial goal and then recursively to the sub-goals, etc., to build a search tree. Nothing very fancy. So here's an example. We have some goal. A implies C implies A and B or C. And then probably we have some implication introduction rule that moves these two hypotheses into the context. Then we might apply an AND introduction rule to split into two sub-goals, A and B or C with the same context. The left sub-goal is, by assumption, trivial. And for the right sub-goal, okay, now we finally have some choice between which rules to apply. We start with O introduction on the left and get a goal that is unfortunately not provable. And then we backtrack. We don't actually backtrack, I'll talk about that. But we apply another rule, O introduction right, and that goal is provable, and we have completed the proof. Okay, so far so trivial. Now let's talk about some extensions to this procedure that we make for Aesop. The first thing we do is that we don't want the usual depth-first search, but rather best-first search. And we implement it in a kind of specific way. So when users register their rules, they also give for each rule a so-called success probability, and these are the blue percentages here. And this success probability is supposed to be a very rough estimate of if the rule succeeds, how likely is it to actually lead to a proof. So for most of these rules here, I've given 100% success probability because they seem like they would always be a good idea. But for the two OR introduction rules, well, we don't a priori know which of the two disjuncts to take, so we just give them a 50-50 success probability. And then based on these success probabilities, we calculate the priority of our goals. So here we start for the initial goal with 100% priority, and then each time we apply a rule, we just multiply the the priority of the parent goal with the success probability of the applied rule to get the priority of the sub-goals. So we start with 100%, then we have a bunch of 100% rules when nothing changes. But here we have a 100% goal, we apply a 50% rule, we get a 50% priority. And if we were to apply another 50% rule down here, then we would get a 25% sub-goal, and so on. Why best first search? Well, basically for performance, right? So this allows us to prioritize likely successful parts of the search and deprioritize likely unsuccessful parts of the search without going so far as to disallow certain rules entirely, right? So we can have low success probability rules in the search database, and they will be applied if we can't do anything else, but they will lead to low priority goals that are then less likely to be picked by Aesop during the rest of the search. And even in our small case studies, we already have some goals that time out without prioritization and that work with proper prioritization. So we have some very weak but experimental evidence that this actually helps in some cases. This specific implementation of best first search I like because it does not rely on opaque heuristics. right? So usually you would have a heuristic like size of the goal or occurrence of certain terms in the goal and so on. The problem with that is that if the heuristic happens to be wrong for some goals that you have, you can't really do anything about it. With our approach, you can always reprioritize goals, or reprioritize rules rather. I can also do this dynamically only for one goal, for example. And so this gives users more control. And this kind of control is one of the main design principles of this tactic. We wanted to give users as much control as possible about the search process. Okay, then we have some extensions here. Don't worry, I'm going to go step by step through this diagram. But just to tell you what this is first. So this is the process that Aesop goes through when it first encounters a goal. It has 3 steps. The last step down here, applying the unsafe rules, is what I've talked about so far. And then we layer 2 other things on top of it. Or rather, we do them before we get to the unsafe rules. And I'm going to talk about these now. Okay. The first thing we do when we encounter a goal for the first time is to apply so-called normalization rules. And these are rules that users, again, give explicitly, and they tag them as this is a normalization rule. One thing about normalization rules is that they can only produce one sub-goal. They can also produce 0 sub-goals, then they close the goal immediately or prove the goal immediately, so then we are done, but usually they generate one sub-goal. A typical such rule is this AND elimination rule at the bottom here. So if we have a hypothesis that is a conjunction, then we split it up into 2 hypotheses and eliminate the conjunction. Okay. We apply these rules in a fixed point loop, and that is what this arrow here means. So as long as a normalization rule applies to the goal, we keep basically going through the normalization rules, which are also prioritized, not based on success probability, but based on some integer number. So we keep applying them basically as long as possible. The big advantage of this is that it allows us to establish invariants that the rest of the search procedure can rely on. Right? So this rule establishes the invariant that after normalization there will not be a conjunctive hypothesis in the goal anymore. And this is something that I think is very nice. The downside of this is, of course, it's a bit of a performance hazard, right? So a fixed point loop is always a bit expensive, especially if rules don't fail quickly. So we need to be a little bit careful which rules we put into the normalization phase. In particular, we also invoke the simplifier, and this is something that we steal from Isabelle Auto, which I think is a pretty big part of this tactic. So the simplifier is very similar to Isabelle's simplifier. It does ordered rewriting with, again, a user-specified set of rewrite rules. And the simplifier is by far the most important proof automation tactic in current lean usage. And in particular, Mathlib, our big mathematics library, defines an extremely large set of equations for the simplifier to use. And many lemmas in Mathlib also then, assume that a hypothesis, for example, are in so-called simp normal form. So they are normal with respect to all these equations in the simplifier. So if you want to use lemmas like this as Aesop rules as well, then I think it's relatively crucial that we integrate the simplifier and that we normalize our goals with respect to the global simp set of Mathlib, for example. Again, one danger here is performance. So the simplifier in Lean 3 becomes relatively slow in deeper parts of Mathlib. In Lean 4, unfortunately, we don't have these deeper parts of Mathlib yet, so I can't test yet whether this is going to be a problem. But I think we might have to do some performance optimization here to actually make this effective. Okay, now, when we're done with normalization, so the normalization rules make no progress anymore, we apply the so-called safe rules. And this is another concept that is lifted straight from Isabelle and another phase in our search. So safe rules are, again, rules that are tagged specifically as safe by the users. And the idea here is that when we apply a safe rule, we consider the goal that this rule was applied to as done. We don't revisit it for the search anymore. So we assume that basically the safe rule generated sub-goals that are equivalent in some sense to the initial goal, or well, they preserve provability to be more exact. Yeah, so this is very nice. A, for performance, obviously. If we can avoid revisiting a goal, that's always going to be nice. The second reason why this is nice is that it allows us some UI features. So specifically, when a proof fails, or a proof search fails, we can report at least the progress that Aesop made using only normalization and safe rules. And if there's a relatively large part of our rule set that is actually safe rules, then this can be quite informative, and users really appreciate having this additional information on what Aesop did for at least part of the search. And then it's usually relatively easy to see, okay, we need to add some more lemmas, we need to add an additional normalization rule, that kind of thing. Okay, and then if none of the safe rules actually apply, we finally move on to the unsafe rules, which, like I said, is what I explained earlier. If none of the unsafe rules apply either, then we discover that the goal just cannot be proven with our rule set, and then that has certain implications for the search tree as well. If an unsafe rule does get applied, then, well, we are finished with this iteration of the search loop, and we will revisit the goal again in a future search loop, and of course we also put the sub-goals that were generated into the goal queue. Okay, so far so good. Now I'm going to talk only relatively briefly, unfortunately for time reasons, about probably the biggest technical contribution of the paper, which is proof search with metavariables. So metavariables, also called schematic variables in Isabelle, I believe, and free variables in some other systems, are both very useful and very annoying to work with for search tactics, and let me demonstrate why. So, suppose we have some goal here involving a less than relation, so we want to prove A less than Z under a bunch of assumptions here. One very useful thing, if you look at the goal, would be to apply a transitivity rule here, and so we do, and we get two sub-goals, A less than X and X less than Z. But the problem with transitivity and similar rules, if you want to apply them in an automated manner, is that you can't know a priori what the intermediate term is going to be, and it's a bit hard to figure this out when you apply the rule. So metavariables can be used to provide an alternative, which is to defer the choice of the intermediate term until later in the search. So we introduce this metavariable $x, and this is a placeholder for some term which we will discover during the rest of the search. Okay, then we apply some more rules. So for example, we could use this hypothesis A less than C here to close this goal, and that seems promising initially. Now that assigns the metavariable x to C, and the thing about metavariables is that they stand for the same term everywhere in the proof and everywhere in the search tree. So this goal here gets updated and now reads C less than Z, which of course is a bit of a problem because it means that this goal is now unprovable. We don't have a hypothesis C less than Z here in the context. So what should be happening is that we can now sort of consider other possibilities for this rule here. Right? So we want to consider the possibility, for example, of using the hypothesis A less than B, which would give us here a goal B less than Z, and that would be a little bit more promising because we have this hypothesis B less than Z here. Usually, if you implement these search tactics using depth-first search, this is relatively easy to do because you can do backtracking here. Right? So when you discover at this point that the search is impossible, you can backtrack this rule, and then if the data structures of your proof assistants are set up to support this properly, which I think most proof assistants are, and Lean in particular certainly has these data structures, then you can just erase this rule, erase the metavariable assignment that it implied, and then try again with a different rule. So this is relatively easy to do. Now, unfortunately, we decided to do BestFirst Search, not knowing that it would cause so many problems with metavariables. And the problem with BestFirst Search is that we need to represent in the search tree all the different possible rules that we could be applying, right? So here, this rule, when we discover that it won't work, we can just, when we discover it won't work, then we can erase it. But in the meantime, we would also like to explore other possibilities. So for example, we would like to explore this A less than B possibility in parallel here, because that's the whole concept of BestFirst Search, that at any point during the search, I can pick any goal from the search tree according to whichever priority it has at the time. Okay, what's the solution here? Well, we propose a very, very simple solution, which is this. So at the point where we apply this rule and discover that it requires a metavariable instantiation, we simply take this goal, which contains the same metavariable, copy it down here, and the intuition here is that because we use this rule to prove the goal, it forces us into a specific metavariable assignment, and so it forces us to prove a particular instantiation of this goal, and so, well, we just treat this goal as an additional sub-goal of this rule. And with this discipline, we can continue the proof. So again, this goal is unfortunately unprovable, but now we can represent the other possibility here as well. And so we have this A less than B rule, and this forces another assignment of the metavariable, namely B. We get another copy of this down here. We get the goal B less than Z, and this is something that we can close by assumption. Now, this algorithm has a couple of advantages. First advantage is that after some terminological work that we need to do, it is a relatively straightforward generalization of the algorithm without metavariables. So in particular, the algorithm without metavariables emerges as a special case of the algorithm with metavariables in a reasonably direct way. The second advantage is that this is highly generic, so it does not depend on the search strategy. We could use it also with breadth first or with depth first as well if you want. And it also does not depend on the logic. So it does not depend on any features of dependent type theory. In our case, you could also use it for first order logic or whatever. Although there are other techniques in first order logic that are probably more efficient than this. That do not translate to dependent type theory, unfortunately, or at least not obviously. And the third advantage of this algorithm is that it is complete. We conjecture. We haven't actually proven this, but I'm relatively sure that it is the case. And it is complete in the sense that if you use a fair search strategy, so one where each rule is eventually applied to each goal, then this algorithm will find a proof, provided that a proof with our given rule set actually exists. So if there is a sequence of tactics that you can apply from the rule set to the initial goal that will close the goal, then this algorithm will find it. The downside, as for many complete algorithms, is performance. So you can probably already see, especially if you have multiple goals here that depend on the same metavariable, or if you have a chain of metavariables where goals depend on each other, then you can get a lot of copying very quickly. And you can also get into situations where parts of the search tree are duplicated at various points. So all of this is not ideal. We have not run into performance limitations yet, but that is only because we haven't used Aesop on very big goals. I'm very curious to see what will happen when we try more advanced stuff. But I suspect that we will need some performance optimization, maybe some caching, maybe some deduplication of goals, stuff like that. We'll have to figure that out in due time. All right, that was all I wanted to tell you for today. Thank you very much for listening, and we have some time for questions.
Thanks for the talk. I'm trying to understand the priorities a bit better. So suppose I have an inductive predicate with 5 introduction rules, 2 base cases, 3 recursive cases. How do I assign the priorities in this case? I kind of want to prioritize the base cases because they close my proof, but what is your general advice?
Yeah, so for the base cases, you can probably give a very high success probability indeed, because they don't generate sub-goals. So if they apply to the goal, if they succeed, then they immediately close it. And so in that sense, they have 100% success probability. For the other rules, it completely depends on what your context is. So what the proofs are that you actually want to do, and how useful each constructor is for these proofs. So for example, if you have an inductive type that represents permutations between lists, and you have an explicit transitivity constructor in there, you probably want to be a little bit careful with that, because then you get very explosive behavior, obviously. If you have an inductive type like the OR type, there it's clearly 50-50. In general, we aren't too fussy about these success probabilities. So in our case studies, we basically use 1%, 25%, 50%, 75%, 99% to just give a rough categorization of how useful certain rules are, and that seems to be enough, at least for our purposes so far.
Thanks.
All right, we have time for one more question, actually. So you'll have to delay it to the break. So I think you were first, so I'm giving it to you.
You talked about the normalization priorities. You said they were integer numbers. How are they decided?
Again, user specified. So when you want a certain normalization rule to be applied early in the process, you just give it a lower integer number. If you want it later in the process, you give it a higher number.
Okay, and is there any way to update these during the proof search?
During the proof search, no. Could be added if there's a particular need for it.
Thanks.
All right. With that, maybe I know there's been a lot of questions, so I think it's a great talk. Let's thank the speaker and let's go to the break.